So this is a new Abaqus script. This tutorial will demonstrate how to start an Abaqus project and build an analysis from scratch. And the example being demonstrated here is that of a English church bell. So at the moment I am just opening some sketches which have been saved externally. We can open sketches in various different file types, so a SAT file or an IGES file or a step file, and the sketches appear in this sketch area within the model file. So this is a completely blank model. We import those sketches into the model file, and then we can commence the process of making a part, and the part will then, once we've decided what type of part, in this case we'll be making a 3D deformable revolved solid model, and it's going to have an approximate size of 1. This is helpful, just it sets the grid size. You can have 10 or 100, it doesn't make too much difference, the approximate size, but it's useful to have a grid that makes sense for the size of the model. This is a rather large English church bell, on the order of several hundreds of millimeters, 600 millimeters in height, so 1 meter makes sense. Now when we import these sketches, it is worth noting that the unit system being used for the raw data here that defines the distances between the points is millimeters, so we will need to define our material property in millimeters when the time comes. I'm just having a look here to see some of the different points in this axisymmetric profile, and then we'll define to revolve that around 360 degrees, and you can see the result here, the solid model. Now because this profile is a series of points joined together with effectively with straight lines, there's nothing other that you can do initially. Then you can see that there are some features on that revolved geometry indicating where the various straight lines connect, or the vertices between the straight lines, i.e. the raw data points. In the future we might wish to produce an alternative profile with curves between the data point splines, for example, such that we have a smooth profile which would be more representative of the actual bell geometry in real life. The next step here is to build a material model. So we're presently building a material model here, and we just need the bare minimum of material properties, so an elastic Young's modulus, and for bell metal you can see the value being typed in here, and a Poisson's ratio. That will allow us to, or will allow the solution, the software, to determine the deformation of the bell when subjected to a particular load, or in this case we'll ultimately be running an eigenvalue study, so we're looking to define some geometry and predict the natural frequencies, the resonant frequencies of this structure in this case. The other property that we need as a minimum, although this isn't necessary for the stress analysis but is useful for determining the mass properties to ensure we've got the mass properties right, is the density. So you'll notice that initially I've entered those values in a meters unit system. Subsequently, later in the video, when we have a look at the mass properties, I'm narrating this retrospectively, so I know what's happened in the future. I'll have to go back and change those material properties to be in kilograms per millimeter cubed, because we've defined in millimeters, and megapascals for the Young's modulus rather than gigapascals. So those are the unit systems when we're modeling in millimeters to be used in Abaqus. Once we created our material property, we have to assign that material property to a section, and then we have to assign that section to the geometry. So there's my section, and now it's assigned to this feature, this geometry within the database, within the model file. Next step is to build an instance of the part in the assembly. It's the assembly on which we apply the mesh, load, boundary conditions, and so on and so forth, not the part itself. And so the next step in Abaqus is to take the part and create an instance of it in the assembly. An assembly can have multiple parts, all of which can be different, or some that are similar. For example, we can have a plate with fasteners, and we might have 6 fasteners around the circumference of a circular disc plate, for example, and 1 circular disc plate. In this case, we've just got the one part, so our assembly just contains one part that's a dependent part, or a dependent instance of the part in the assembly. Next step is to define, or next part of the process, to define a step, and you can see I'm working through the module list in the top left hand corner, from part to property to assembly step. And so this is a linear perturbation step that we're using here, so we're just using a small perturbation essentially to predict the natural frequencies in the same way that you would do so experimentally. I'll define the nature of the perturbation here with a description which should be identified. We could have multiple steps, for example, within our model file. We could have steps that can be suppressed and resumed depending upon the specific nature of the model. We can have also multiple models within our model database, and so you can, once we've built one model, we can copy that model and create different properties that might include having a different step or a different loads and boundary conditions and so on. So Abaqus is quite powerful in that respect. Speaking of boundary conditions, I've now progressed to that stage, and I'm going to define a fixed or a pinned boundary condition here, which will be effectively a pinned point at the top of the bell, which will be representative of how it's installed in the bell tower. And so I can select this face or this point on the top, and I can apply a pin to it. Initially I'll be doing a free analysis, a free vibration analysis. So once I've created this boundary condition, which as you can see I'm going to select for it to be pinned, so no translations, but we allow rotations, I can then suppress that boundary condition temporarily and resume it when I want to study the effect of the boundary condition on the vibration of the part. So I can use the manager in most cases for these parts. You can see I'm having to drag these little GUIs in from the top because I was running on 2 screens, so every time it opens a new one it puts it in the top screen. I have to pull it down to the bottom screen. That's what's happening. So back to the loads module, and it tells me there that I have to apply this kind of property to a dependent part instance. So I'm meshing now. First, so I create my mesh at the part level in the case of a dependent part instance, so that if I had multiple parts or multiple instances of the same part within my assembly, I wouldn't need to mesh each one individually. I would just mesh at the part level, and then all of the parts within the assembly have the same mesh in the event that there are multiple parts. If I wanted to instead have independent instances, then I could mesh each of the parts differently. So if you knew that you had different stresses in the same part because of the different location that they were in, it might be the case that you wanted to have an independent part instance and then you could apply a mesh individually to each of the parts. But yeah, in this case it makes little difference. We go with the default dependent part instance, so the mesh is applied at the part level, and we've only got one part within our assembly. So now I can experiment with the seed density essentially. So I'm introducing a different number of seeds, or different seed size, and then you can see the result of creating the mesh, which is a hex dominated mesh. I can check the mesh properties here by selecting the part, and this will return some information about the quality of the mesh. I can highlight the mesh elements that have got high aspect ratios, for example, which I might want to avoid having. And I can also see the results of the mesh in terms of the number of elements and number of nodes and so on in the command prompt window at the bottom of the screen. So it tells me I've got this number of elements, and also gives me some information about them. Now I can make the mesh more refined by changing the seed separation to make it smaller, It will give me a warning that I'll need to delete the mesh if I change the seed size. OK, no problem, and then remesh the part. And now I've got a finer mesh. Again, I can have a look at that. These are all hexahedral elements. In this case, I haven't yet changed the mesh properties. I do have some steps in this profile. It needs a little bit of cleaning up, so in subsequent analysis I will refine the profile to remove some of the steps. The step around that crown, around the shoulder area there, is what's causing the issues with the mesh that we're being warned about. And you can see that in a moment here around that shoulder area. So there are some features to help us diagnose the nature of the mesh. We can change the errors and warnings appropriately. We can define for ourselves what we consider to be a high aspect ratio element. So we're essentially in control. Warnings are acceptable, errors will give us problems during meshing. If we have another look, as I was explaining previously, at the root cause of the issues that we're observing, we can see that there are indeed some step regions here with these two data points. These data have been collected experimentally, and there is a finite resolution with this measurement technique that leads to this step feature, which is clearly not a real feature on this smooth cast bell structure that we're investigating. So we can fix this up by removing one of the points manually and reconnecting the lines between the points. We're just interrogating currently the values of the XY data. And opening up the raw source data, which is in the form of an Excel spreadsheet. Which will be shared as a packet of information in association with this video for users working on this in the future. So Excel's just loading those profiles now, and here they are. And we can see, albeit it's a different aspect ratio just because of the way Excel plots, there's the feature that's causing us the problem within Abaqus. So back to the mesh, and then moving into the job module, we can create a job, give it a name, choose which model we're going to use to build the job from, give it a description, similarly to how we gave the step a description, so that we know when we have multiple jobs within our model database or associated with our model database what each one is doing. So this is going to be looking for frequencies up to 5 kHz from this structure. And here you can see the jobs sit slightly outside of the model database in the analysis part of the model tree. And again, we can use the job manager, and each of the jobs we can open a monitor for each of those jobs. So at the moment I'm using a relatively low powered PC here. It's just takes a little while when we submit a job to the solver. But here's the job manager, so all of our jobs will be listed in here. We've got one job presently which is running, and if I open the monitor for that particular job, it'll give me an indication as to what stage the job is up to. So it's been submitted for analysis. It's now interrogating the mesh. We get the same warning that we found when we interrogated the quality of our mesh, i.e. we have 342 elements that are distorted. At the moment we have no errors. We've got an output database that gets created. Once the job is complete, we've got a data file, essentially it's a .dat file, and a message file, a .msg file associated with each of our jobs. And here's the information that's being printed to the message file, including some of the information that we're already aware of: the number of elements, number of nodes, the type of analysis, various other important information, when the job started, how long the job took, how much CPU time was used, and so on. So the job is now running, and it's completed the check. So the first step was to complete a data check. It's worth always doing a data check before we actually do a full submission. It will check that the model makes sense, that we've got a material, that we've meshed the geometry, that we have a section, that the section's been assigned to the region in the geometry, and so on. We should always do a data check first. It will also write the input deck that gets submitted to the solver when we hit the continue button. If we've already completed a data check, we can then hit the continue button within the job manager. If we're starting from scratch, we hit submit, or if we hit submit after having done a data check, essentially the first thing that it does is recomplete the data check. So from the manager, data check first, wait for it to complete. There will be an ODB created as a result, but there'll be no stress results within that, or no frequency results in this case within the output database, but there will be an output database, so we can go from the data check to the results file and have a look in the visualization module. But until we've actually completed a solution, then we won't have any stress results or frequency results to interrogate. What I'm doing here at the moment is just having a look in the task manager to see what processes are running, because once we're running the job, of course we should be using plenty of CPU memory. You can see that here, CPU percentage implementation is very high and memory usage is high. The solution is swapping data from RAM to the disk, and so the resources are quite heavily used. And that's a good indication as to whether or not the solution is still running. So we use the task manager to validate that the job's still running. Now when the job's running on the solver, I can still go in and make new model files. I can still use Abaqus CAE, the graphical user interface, in the background essentially, or indeed in the foreground. Leave the solution running in the background. So now I'm going to go in and create a duplicate model file here from the one that we've created, and make some changes to that. Try a different profile, for example, change the seed size, maybe use some different boundary conditions. These are the things that we can do within our model database because of the fact that we can have multiple models within the model database that allow us to use Abaqus, and then we can park these jobs up on the solver and it will work through them one by one. I'm just having a look here in the folder where we're working from. Here you can see the CAE file, that's the model database, the solve file here, the DAP file, the message file, the output database, which should be being written to as the solution progresses to completion. Just checking everything looks sensible, and now I can copy my model. And you can see when the new window comes up, gives me the chance to rename it, so I'll call it smooth, because I'm going to change the profile to make it smoother, so we can eliminate that step problem that we have observed. And then now it's open, I can expand it in the model tree, open the part that's also been copied. All of the things that were in the previous model have been copied across, and then I can edit the part to change the profile. So of course, now that I've got a solution running on this computer, everything is a little bit slower. CPU and resources are being used, so for me to be modeling at the same time means that I have to be a bit more patient. And here you can see I can drill in and change my section sketch. So you saw previously I had multiple sketches already loaded within the model database. I've got a complete profile smooth, a complete profile smooth boundary, and my full profile, which is the manually entered data points. So the smooth and smooth boundary profile are quite similar. They've been created from the raw points but using splines to join them together. And so here we can come in, open the sketch up. This is the original sketch. Let's remove all of those. And then we can grab that new section, that alternative section. Of course, we haven't regenerated the part yet, so the 3D geometry still sits in the back of the sketch there, but now we have our new profile in here. It's a little bit different. Some of these endpoints aren't joined up. We've got a line here indicating the axis of symmetry, so we'll need to edit that a little bit, which I'm doing now. Remove that line for the moment. Join those two data points up, and you can see there are very few points in here. Actually, it's just a set of splines, some straight lines towards the top, and it gives us a warning that we need a construction line to indicate the center line. So we can add that one in manually. We can have a vertical line for construction. Notice if I press and hold, the little extra features from the black triangle in the bottom right of any icon become available. So this is an infinitely long vertical line that I can snap to that data point at the middle of the crown, and then finish the sketch. I get a warning that the feature has been changed, it needs to be regenerated. I can do that from the model tree. At this moment we have a look at the assembly, it's also regenerated there, and we can go back to the mesh functions and apply some seeds. Remember, it's a dependent part instance. Change the seed size, run the mesh, and it takes a while. Remember, we're still running the solution at the same time on this machine presently, and you can see immediately there are lots of errors now with our mesh, which we need to resolve. So we can change the seed size, try to have a look at the impact of that. Delete the old mesh. So we have now a coarser mesh, larger global seed size. We can also partition the part, we can introduce bias seeding along certain edges, we can have different global seed size for different regions within the partitioned part. There are many ways in which we can look to further refine the mesh. There are indeed applications such as HyperWorks meshing just for the job of building meshes. Abaqus meshing is okay, but not one of the more powerful industry standard meshing capabilities. We still have these mesh problems with these hexahedral elements, even with a coarser mesh. And instead of the coarse mesh, we can actually then have a look at changing the nature of the mesh elements. Tetrahedral elements are more difficult to get a good quality mesh from. They can produce better results for stress analysis, but for the sake of getting a good mesh, a tetrahedral element type is a more effective element. So we'll explore the capability of that once we've had a little look through the assembly here. So we change the mesh type, and rebuild the mesh. And now we have a mesh made of tiny pyramids rather than bricks. We can make that more refined. Regenerate. And now we have a much more refined tetrahedral based mesh. Let's have a look at the quality, and you'll hopefully see that we have still just a few small warnings, but nothing like the problems we had previously with the huge numbers of errors. These are just around the inside where we have some high aspect ratio elements. We can resolve those, as I mentioned before, with various techniques, including having some more refined biasing around that component in that particular region. And at this point we can build a job from this based on the previous job, submit it to the solver, and have these two running simultaneously, and we'll do so in a moment. So build a job from the alternative model, which is the smooth model database. Give it a different name. Continue. Description as before. Smooth mesh, and submit. Run the data check, and we get a warning. So that's the power of the data check right there. So when we copied the model across and changed some elements, we changed the profile, we need to go back and reassign the section to the region in the part which needs to have the material properties associated with it. So that's a really good example of the power of running the data check before we go and run a full model. So we just go back into the property module, reattach that section. You'll notice that when we reattach the section, the geometry itself turns green, which indicates that it's happy with the changes that we've made. And now we can run the job. Again, run the data check, and we're good to go with the model in the future. We might wait until the other one's finished solving before we run this one, or we could just get them to both run and queue them up. We'll have a look in the monitor in a moment. And you can see that that job, the Datatech job, is currently running and will complete shortly. Hope that's been a useful video. Thank you. Have fun with Abaqus.